A student asked a question about a drum rotating with a diameter of 0.50 meters and rotating at 1,600 revolutions per minute, plus or minus 100 revolutions per minute. The question asked what the speed of the rotation of the drum was and the absolute uncertainty in that value. Well, here's the question all laid out with a diagram showing the diameter of the drum and the numbers that we need. Now, what the question's asking for is the speed of the drum at the edge. So we can add this to our diagram. That's what we're after. The speed of the drum at the edge. Now we know we're going to be using the equation speed is equal to angular velocity multiplied by the radius. We're going to be using that. We need to be careful because we are given the diameter, not the radius. That's one thing we need to watch out for. The other thing is that our angular speed, angular velocity, or angular frequency is given in revolutions per minute. So we're going to have to convert that into radians per second. So let's do that conversion first. 1,600, and I'm going to write down revolutions divided by minutes as the unit. Revolutions per minute. Now what I need to do is get rid of the revolutions part. And I know that 1 revolution is equal to 2 pi radians. And that means that I can now cancel the unit revolutions. Remember that as long as the top of a fraction and the bottom of a fraction equal the same thing, the fraction has a value of 1 and has no dimensionality, has no overall dimensionality. So by multiplying my number, the revolutions per minute, by 2 pi radians divided by 1 revolution, I haven't actually changed the number, but it means that I can cancel those units of revolutions. Well, now I've got radians per minute. I want radians per second. So I know that there is, in 1 minute, there is 60 seconds. And just as before, we can now cancel the units minutes. And we are left with the units of radians per second. They're the only units we've got left, which is exactly what we want. So the computation I'm doing is 1,600 multiplied by 2 pi and divided by 60, which means my units will be radians per second, which is exactly what we need. And when you type that into your calculator, that gives you approximately 167.55 radians per second. Just gone off the edge of the screen there. There we go. Now, notice I've kept some extra digits here. I know I'm going to be rounding my final answer to just 2 significant figures, perhaps. At least that's the precision of this diameter. However, if I keep some extra guard digits, these extra digits, 3 extra digits on this number, then any rounding errors that might accumulate, I'm going to round away from my final answer anyway. So always keep a few extra guard digits in your calculation. So next up, we're going to calculate our speed. Remember, our equation was speed equals angular frequency multiplied by radius. Well, the angular frequency we've calculated as 167.55 radians per second. But the radius we haven't yet calculated. We have a diameter of 0.50 meters. And so if I halve that, that's going to be my radius. And if you type that into your calculator, you get about 41.888. Again, I'm keeping some extra guard digits here, meters per second. Now let's have a look at those errors. So a principle with errors is that if quantities are multiplied together, you can add their relative uncertainties, or you can add their percentage uncertainties. And the notation I will use for relative uncertainty or percentage uncertainty is an epsilon. That is to say that the relative uncertainty or the percentage uncertainty in U is equal to the percentage or relative uncertainty in omega plus the percentage or relative uncertainty in R. Well, we are not given an uncertainty in R, so we can assume that there is no uncertainty in R. And that means our percentage uncertainty or our relative uncertainty in U is equal to our percentage uncertainty or our relative uncertainty in omega. Now, the relative uncertainty in omega is the absolute uncertainty in omega, which is 100 revolutions per minute, divided by the mean value, which is 1,600 revolutions per minute. That gives you a relative error of 0.0625 or a percentage error of 6.25%. I'll write it as a percentage error. Sometimes you'll see people write multiply by 100% here. But given that percent means divided by 100, they're actually writing multiplied by 100 divide by 100, and I find it a little bit pointless adding that there. So this is the percentage error, and if I just divide it through by 100, which would mean exactly the same thing, that would be our relative error. Now that's the relative error or percentage error in omega, which is also the percentage error or relative error in U. So the absolute error in U is equal to the percentage error, which this time I'll write it as a decimal, 0.0625, multiplied by the mean value, which was 41.888 meters per second. And that would equal, and we've got it written here, 2.618 meters per second. And that's the absolute uncertainty. And now for some rules. Now, obviously, the rules are different at A-level to everything else in physics. In the real world of physics, we'd be quite happy giving uncertainties to one significant figure. And that's pretty normal. Unless that significant figure is 1, and as 1 is the least significant figure, then we would give our uncertainty to 2 significant figures in those cases. But because that rule is a bit complicated, in A-level physics, we tend to just give our uncertainties to 2 significant figures. So I'm going to fill in my answer now, and I'm going to already fill in my uncertainty 2.6. And I know the unit is going to be meters per second at the bottom there. So if that's the, let's put U equals, so if that's the uncertainty, that tells us how many digits we round our mean value of the speed to. So you can see that we want to match the number of decimal places. So here we have 41.888. We want to round that to 41.9. And as a rule of thumb, what you do is you make sure that the error part is in standard form and then match the decimal places. That's how you make sure that your 2 answers are to the same precision. These 2 answers have the same precision. The error and the mean value here are to the same precision. It's a bit of an odd rule and it's a bit difficult to get your head around, but with practice, you get used to it. And it starts to make a bit of sense after a bit of practice. Now you may say, but hang on a minute, the diameter was only given to 2 significant figures, so surely we should give our answer to 2 significant figures. Surely you'll be thinking to yourself, you should give your answer as 42 plus or minus 3 meters per second. And I'd love to tell you that that is correct, because it really is correct. There's nothing wrong with that. As I said, giving uncertainties to 2 significant figures, if the significant figure is a 2 or a 3 in this case, is a little bit, you wouldn't do that in the real world of physics. It's unnecessarily precise error. However, in A-level physics, to keep it a bit simpler, then we would be quite happy to use a 2 significant figure error. When you're dealing with errors, that determines how many significant figures you give your answer to, because you're already handling the uncertainty in your number in the error. So that's what decides what number of significant figures you use. If, however, we were not dealing with errors, then the usual rule of the least precise datum is what determines the precision of your final answer would apply. When we're dealing with errors, then we use this rule. Make sure the precision of your error matches the precision of your number after rounding your error to 2 significant figures. So this answer would be marked as correct. This answer you could potentially lose a mark for, even though there's nothing wrong with it.